All right, for our next presentation, I'd like to welcome the team from Revolution Aerospace, Melissa, Alexiou, and Huang. So Melissa is the Head of Strategy and Marketing at Revolution Aerospace. Her passion includes leveraging her aviation knowledge to progress UAS and UTM through broad stakeholder engagement and communication. Prior to working with the Rev Aero team, Melissa led a progressive team at Air Services Australia with the Integrated Airspace program. Her experience extends from leading projects such as the deployment of drone detection capability across Australia's 29 online air traffic control towers through to researching alternatives to high-frequency voice communication systems. Huang has served as the product development lead at Rev Aero team since its founding in 2021. Prior to this, Zi spent 2 years as project manager and software developer at Nova Systems Asia, where he led the technical team in Singapore and was responsible for the development of the prototype UAS traffic management system as part of the international UTM R&D consortium co-founded by the Civil Aviation Authority of Singapore. Everyone, please welcome Melissa and Zi for their presentation on UTM in Australia and beyond.
Thanks, Isaac, and congrats again for your award last night. Very well deserved. So Zi and I think I can speak on behalf of both of us. We're both very proud to be here today. And to give you an idea of the theme of our presentation, it is centered around the considerations required for a minimum viable UTM system. So to kick off, we'll just give you a bit of a background of the presentation. So we'll start with a bit about Zi and I and our experiences in UTM. We'll also recap on UTM and its journey since its inception around the world and within Australia as well. We'll also give a bit of a summary around the utility of UTM, why it exists and the benefits it will bring. And then subsequently we'll talk to some of the challenges, opportunities and lessons that we've learnt along the way, and then wrap up as well. So without dragging this on, a bit of a recap of our background. So I joined Revolution Aerospace as the Head of Strategy and Marketing about 6 months ago, and hopefully throughout the conference you've seen some of that and have gleaned a little bit more about what our organisation has done in this space. So my experience is really deep-rooted in aviation, international business and in management. So I started out with a charter airline. I managed a fleet of operations of turboprop aircraft, and then I got the opportunity to move to Air Services and got to see the other side of the picture where I managed slots into our major ports. I also worked at the ATSB and I worked with some incredible investigators there. And then I moved back to the drone surveillance program and integrated airspace program with Air Services. I've had the privilege of working with some exceptionally talented people in our industry and across my career, and again, back at Revolution Aerospace, working with a team that can solve what might seem like a complex black hole, but really create an impactful path forward for our RPAS industry. So what does all of that mean for UTM? It means that we can leverage a lot of what has occurred in the ATM space and apply that to UTM, or purposefully choose not to, and we'll hopefully describe that in a bit more detail soon. So that's a quick recap of me. I'll hand over to Zi and we'll do a bit of a contemporary dance up here for you throughout the presentation.
Thanks, Mel. Good afternoon, everyone. I'm Zi. I'm the product development lead at Revolution Aerospace. Unlike Mel, I've had a relatively short aerospace career so far after graduating in 2017. So I joined Nova Systems Australia as a system engineer in the same year and had the opportunity to work across several projects in the civil and defence domain. So one of the more interesting projects I was involved in was Australia's very first UTM demonstration for disaster management. That was done in 2017. So in 2018, I relocated to Singapore to support the development of a prototype UTM system for the Singapore Ministry of Transport. So over these 2 years, my team and I conducted many flight trials across Singapore and in order to help define Singapore's UTM concept. There were many challenges and lessons learned along the way, and today we'll hope to share with you some of these challenges, and we hope you get something useful out of it.
All right. So this is a very modern history lesson dating back to 2014. By aerospace standards, it's still very much a new and untested space. So to begin, back in 2014, NASA led some early research into UTM. They recognized the need for revolutionary change in air traffic management and to enable the demands of industry. So we've heard throughout various participants here today what some of those activities might be. Things like package delivery services, medical deliveries, and generally enabling UAS operations at scale. So as Rowan mentioned yesterday and Brendan have mentioned, there's no way that we can foresee all of the operations that are to come. And so it's about creating a space that can enable that. So NASA kicked off a technical capability level program with industry exploring options for the design, prototyping, and trialing of UTM systems. Not long after, the FAA stood up the UTM pilot program and CESA established their U-Space program. So these activities were set out to define and develop blueprints for how new services could be offered that rely high levels of digitization and automation. And as such, we've got a broadly harmonized concept for UTM across the globe. Since 2014 as well, what we've also seen is global investment in UTM has continued to grow. Reports suggest that the UTM market will reach $2 billion by 2025, and that actually excludes the market value for emerging technologies such as eVTOLs and other platforms. And that is set to be around $10 to $20 billion of investment dollars already invested in that space. So overall, a lot of money has been committed here. So what does that mean? Some takeaways from this to date. The future holds a diversity of operational applications, which current ATM systems weren't built for and will struggle to accommodate. Mature markets, such as aerospace and others as well, are already highly valued. So new ideas seem attractive for investors. And additionally, there's lots of activities undertaken to help refine and define what UTM is. But what remains is the consensus to its implementation and actually implementing it. So a bit of our lived experience and a snapshot of UTM. So in Singapore, as Zi mentioned, the T under Zi and our CEO Terry led the safety and trial management of a UTM. They provided a platform, they gained insight into the development of UTM technologies and the broader ecosystem. They investigated the role of 4 and 5G in supporting safe control and monitoring of UAS operations in a metropolitan environment. They also conducted live flight trials, capturing connectivity data and understanding what might corrupt communication and navigation's performance. Then back to Australia. My previous role was at Air Services, as was Christian Cruikshank, who is our CTO, and we've both had the privilege to drive and support the development of Australia's UTM ecosystem. That's through the Flight Information Management System, through drone surveillance, collaborative traffic management in the stratosphere, and the drone rules management system. And as we heard from Diane yesterday, that's a really key pillar to the UTM ecosystem as well. So we're familiar with the nuance that our geographical borders can present in UTM, and we'll talk to that in a bit more detail as well. So now I think it's important to briefly talk about the art of the possible. What is UTM set to deliver? And I think that's critical before we talk about how we can enable it. So UTM is seen as a solution to high-density drone and advanced aerial mobility operations, delivering packages, medical deliveries, and enabling low-altitude operations, making sure that they're all managed safely, and also considering the new means of human involvement as well. UTM will support operations in geographically geofenced areas. Theoretically, it'll be more economical in the long term than road transport and potentially other forms of transport. UTM will be essential to enabling hundreds, if not thousands, of use cases that have been dreamt up and are still to be dreamt up. UTM can be portable. It can support operations of micro, hobby, commercial, all the way through to large operations. And it can provide communication, navigation, and surveillance below 10,000 feet. So to enable safe UAS operations, we've got to consider everything from operations contained in airspace, where there are typically no air traffic control services, through to operations conducted wholly in controlled airspace. And while there are many considerations with building a UTM, today we're only going to focus on 2 key areas, and they're regulatory and technical, because we haven't heard enough about regulatory and technical today. So to kick off with the regs. in order to enable the systems, the services, the technology, and their commercial implementation, they're all underpinned and bound by supporting and enabling policy, regulations, and standards. We need to consider how UAS will be integrated with traditionally crewed aircraft and the UTM architectural models that can support that. So as I've mentioned, the future holds a diversity of operations, and a traffic management system needs to be able to cater to those aircraft, and particularly aircraft with a variety of different characteristics, if they're going to be able to share the same airspace. So across the globe, different countries have applied a different approach to this problem to integrate UAS into their airspace. With today's air traffic management system, it's based on a centralized architecture, where a single entity is responsible for managing the air traffic and all of the services are provided from therein. In air traffic management, that supports the safe and efficient communication of all flight authorizations and planning as it's managed by one organization. On the other hand, when it comes to adapting to new technology or market changes, the lack of competition in that central structure can make it very slow to adapt. If that approach were adopted or applied to UTM, we would likely see that UTM and its participants experience those same challenges that the ATM world is experiencing. Across the globe, UTM have considered a federated or decentralized approach, and in initial stages, that was adopted by the FAA in their early systems development. Federation allows for distributed management of airspace, where different entities can collaborate to maintain a safe and accessible environment. It's a mixture of distributed and centralized components, and that enables competition. So a plus for that architecture means that we get the flexibility to adapt to the pace of change, and we can implement innovation on demand. Some of the downsides include that it becomes a little bit more complex, and communication protocols across those traffic management decision areas are a little bit tricky because that's now distributed over multiple service providers. That also might have an influence on the regulatory standards and the technologies that are applied. So care really does need to be taken when we are developing standards and regulations in that space, because sometimes making them too prescriptive or overbearing has the opposite effect to innovation. So instead of driving competition, services might now only be provided to those that have the adequate market position. But in the end, the main goal with any architecture is to ensure safety. And simplistically, that means ensuring two vehicles are prevented from occupying the same airspace at any given time. In Australia, the proposed federated architecture is composed of multiple interoperating services, and that's the centralized government service. You might be familiar with the Flight Information Management System, and that provides the directives, the constraints, and the requests, enabling that system to be market-driven. So while there is still a lot of work to be done in that space, the key outcome is ensuring safety, fairness, and equitable airspace access. So UTM also depends on interoperability of services and based on that interface standard. While there has been significant progress in this space, and Zi will talk to this in a bit more depth shortly, some of the considerations that remain are what standards need to exist to support interfacing with ATCs and ANSPs who manage the control airspace. While most of UTM was designed to exist outside of control airspace and at low level, as we've spoken about, the diversity of operations continue to grow, so we will need to be able to integrate with ATM. And what will that certification process for UTM architecture and services look like? It's likely to be commensurate with the safety criticality of that service, and it may be applicable to draw from relevant crewed aviation frameworks and standards to assure UTM on a performance and risk-based criteria. So you might have also seen last month, Israel announced their Hermes Starliner UAS as the first ever to achieve type certification and to fly in controlled airspace after a 6-year process. So while it had already been in operation for a number of years, it even operated during the Brazil World Cup in 2015, at that time it still required segregated airspace. So as we've heard, companies are working with the regulators to partner and test and verify their technologies to meet these new standards. The case for UTM that can manage the diversity of operations continues to grow. So lastly, this leads to automation. So we've mentioned UTM is all about automation. We start from a low to no automation environment where humans are directly responsible for the safe operations of aircraft, and all crewed aircraft are responsible for avoiding each other, and drones are limited to fly within line of sight of a pilot. In a low automation environment, regulations, policies, and obtaining approvals are a really manual process, and that requires the individual professional assessment, as we've heard today. But over time, as we increase our application of automation, we start to progress the automation of beyond visual line of sight of operations, so moving from that low-density airspace into controlled airspace. We start to enable drone fleets to operate at scale. And of course, the dreamt-up end state of full automation, where technologies are proven and certified and are available for use in all conditions and at all phases of flight. So again, that begs the question, how do we ensure our regulations are flexible and fit for that stepwise approach in automation? And of course, overseen equitably across the country. So today we've been proposed an option, a regulatory readiness level approach. That might be the solution, but the other alternative is to ensure that industry are collaborating together as well before proposing that problem back to the regulator. And again, these challenges aren't insurmountable, but they do introduce several new elements that need to be assured and tested before they are widely introduced. They can't be worked on in isolation, so now I'll hand over to Zi, and he'll walk us through the importance of interoperability when it comes to technical implementation.
Hey, thanks, Mel. To appreciate the technical challenges involved in implementing a UTM system, so let's have a look at the key ingredients needed to develop a minimum viable product. So while we acknowledge that there are many technical challenges that need to be solved in order to develop a fully fledged UTM system, in the interest of time, we'll only look at a few of them today. The term UTM was actually first defined by NASA back in 2014, following FAA's roadmap to integrate civil UAVs into the national airspace system. Now, the fundamental goal of UTM, as defined by NASA, is to enable safe and efficient low-altitude airspace operations. Now, for the design of a UTM system, the need to optimize for safety and efficiency is becoming increasingly more important as short-duration and high-volume low-altitude operations become more prominent in our congested airspace. Defining the concept of operations for UTM is a critical first step. So questions like, who are the users? What's the operating environment? And which common framework to consider must be top of mind when defining our UTM architecture. So critically, a UTM system must be designed with interoperability in mind from day one. This is necessary to foster industry collaboration, which is key to enabling global harmonization. Just like how TCP/IP revolutionized networking, thus giving rise to the internet, a common UTM standard is key to enabling mass adoption of UTM and complex UAV operations. So currently there are several open standards and guidance documents available to inform the design of our UTM system. So some of these are listed above. A fundamental UTM challenge is the large number of conflicting flight operations the system must deal with in a real-time environment. So these operations, this is particularly true in urban and suburban environments where traffic density can be significantly high. So we need smart routing and scheduling algorithms coupled with a level of automation to ensure that airspace operations are efficient and conflict-free. Now, the choice of route design largely depends on the geographical location where the UTM system will operate in. And generally speaking, two common approaches may be considered in the design process. Now, the first approach employs a structured network of predefined routes to manage UAV traffic capacity and flow. This approach is akin to our road infrastructures, where a UTM network is formed by interconnecting corridors and junctions. The second approach employs a free flight strategy to determine conflict-free routes without needing to pre-impose a particular network structure. This particular approach is commonly used in motion planning, so within robotics, where path planning is done incrementally and locally. As an example, the image above is a simple UTM network developed for Singapore. So it uses a hub and spoke network structure, which was optimized for postal delivery operations. While there are many performance trade-offs between these two methods, we can overcome many of their bottlenecks with better performing algorithm and hardware. However, the choice of optimization strategies selected for route design remains an ongoing challenge in UTM. Several key questions like, how should we optimize the shape of our UTM network to achieve some desired margins of safety and efficiency? Should we optimize for travel time, perhaps ground risk, or maybe noise impact, or perhaps the overall utilization of the airspace to maximize the number of daily flights? If we do manage to resolve these multi-objective optimization problems, we still need to figure out how close together we can fly these UAVs while maintaining some target level of safety. To answer some of these more safety-critical questions, we'll need to understand collision risk and establish communication, navigation, and surveillance performance requirements for UTM. This would allow us to quantify the safe separation distance between UAVs to meet a desired target level of safety for the UTM airspace. Collision risk is formally defined by the International Civil Aviation Organization, or ICAO, as the expected number of fatal accidents per flight hour, so where each collision is considered as 2 fatal accidents. However, collision risk don't necessarily result in fatal accidents with UAVs. This means that the collision risk will need to be treated slightly differently in UTM. In the ATM environment, variations of the right collision model, as mentioned by Dr. Terry Martin earlier this morning, have been widely used to mitigate collision risk between piloted aircraft pairs. Recent studies, notably the work done by Callanan and Dr. McFadden in 2021, have made significant progress in extending this model for use in UTM environments. So suppose we want to work out how close we can place a set of parallel tracks to maintain some target level of safety for our UTM network. We can use the extended collision risk model to determine this analytically. So as an example, let's say the target level of safety required for aero package delivery operations is 10 to the -4 accidents per flight hour. And let's also assume that 1 in 1,000 UAVs are navigating poorly in the airspace. Then a minimum separation distance of just under 90 meters is achievable for our UTM network. So that's illustrated on the diagram above the blue line. So we have actually made some assumptions on the navigation performance of the UAV in order to estimate collision risk. But how do we go about determining navigation performance in the first place? So let us briefly explore required navigation performance, so which in simple terms, it means it dictates how good an aircraft can maintain to its assigned route. So unfortunately, there are no formal definition of RMP within the UTM context. For ATM, however, RMP values can be as low as 0.1 for aircraft navigating in congested airspace. So that means the aircraft must maintain within plus or minus 0.1 nautical miles of its assigned route at least 95% of the time. So that actually equates to plus or minus 600 feet, which is much too large for most UTM operations, especially in urban environments where UAV might need to land in between buildings that are much less than 600 feet apart. Therefore, some effort is required to define more appropriate RMP values for UTM. Again, Dr. Terry Martin has presented a lot of work on this at the recent ICAO Drone Symposium in 2021, as well as 2017. The accuracy requirement in RMP requires us to mitigate a 95% total system error of an aircraft. This means that the total system error needs to capture the true positional offset of the aircraft at least 95% of the time. So this actually provides us a basis to conduct flight trials to directly measure the components of total system error of the aircraft, and therefore the navigation performance of different UAVs across different environments. So the above graphs are some of the results obtained from 7 independent flights across Singapore. So I was involved in those trials. So our study actually shows that the DJI M600 can achieve a 95% total system error of about 2.5 meters across the 7 urban locations that we operated in. So it is very location specific. In comparison, the total system error of DJI Phantom 4, which is a lower cost system, can achieve about 3 meters. Although these results provide us some insight into navigation performance within the UTM context, there are still many challenges outstanding to fully specify RMP for UTM. So some of the key challenges include specifying RMP value for UTM will need to be substantiated by conducting many, many more flights across a larger permutation of environments and UAV types. Flights will also need to consider nominal and off-nominal operating conditions where the effect of wind is non-negligible. Estimating navigation system error in poor signal environments, such as urban corridors in between buildings, becomes challenging even with the use of real-time or post-process kinematics for ground truth positioning. For example, the sub-meter positioning resolution we obtained for many of the flights that we conducted near tall buildings cannot be reliably used to estimate total system error. So to give an example, I think we did probably up to about 15 or 20 flights. We were only able to use about 7 flights to produce some of those results on the slide. Obviously, an alternative approach to measure ground truth tracks will be needed in order to help solve this challenge. Lastly, RMP only specifies the requirements for lateral navigation performance, with some extensions that include the vertical component. However, longitudinal navigation performance, or in other words, timekeeping performance, is not yet defined. Adding to this, current UAVs, like the DJI platforms, do not support time-based waypoint operations. This makes it extremely difficult to assess timekeeping performance of the UAV along its assigned route. Additional features, including time-based waypoints, will need to be developed by OEMs to ensure that their platforms are UTM ready. So these are some of the key challenges we'll cover today, and I'll hand back to Mel to wrap up this presentation.
Thanks, Zi. So there you have it. Now you can build your own minimum viable UTM. But in case you were asleep after lunch, I'll just give you a bit of a recap. So some of the key elements to consider, obviously the infrastructure requirements are key. So making sure that there are ground facilities that are enabling the launch and recovery of UAS, and that enables that continuous development and integration. Also, ensuring that the adoption of UTM interoperability and data exchange standards are there. So that's melded through the desired architectural model for each country, and integrating that UTM with the existing ATM services. Next, continuing efforts to establish communications, navigation, and surveillance performance and collision risk requirements for all of the different UAS systems and their operating environments as well. And then finally, we mentioned the need for a lot of data. So that will help optimize the route design for safety and efficiency. So some of the data can include things like cellular network data, weather data, noise maps, building and terrain data. And it's unlikely that one organization can provide all of those data services, so being able to work with the public and private stakeholders to collaborate and ensure that we're solving those problems in harmony. So overall, we've raised a lot of questions, and I'm sure you've got a lot of questions for us as well. But if you hadn't noticed already, we do have a booth outside.